Dear students, welcome to today's class. In today's class, we shall be discussing a topic that is addition reactions of conjugated dienes. So let us study it in detail. Let me share my screen to present the PPT that I have prepared. Okay, so here it is, addition reactions of conjugated dienes. First, we will study electrophilic addition, and as an example, we will take addition of HBr to 1,3-butadiene. As you know, 1,3-butadiene is a conjugated diene. So I'm sure all of you can write the structure of 1,3-butadiene. So let me write it here. CH2 double bond CH single bond CH double bond CH2. This is 1,3-butadiene. Now, when we add HBr, it is an example for electrophilic addition. It is found that we get two different products. First product is CH2, CH, Br, CH2H. That means from this molecule, hydrogen part is added to this carbon and bromine is added to the adjacent carbon. Since the addition has taken place on adjacent carbon atoms, this kind of addition is known as 1,2 addition. 1,2 addition. And the actual name of the molecule, we can write IUPAC name. So what will it be? Now it is only butene, substituted butene. So if you start numbering the butene from here, 1, 2, 3, 4. So we can write it as 3-bromo 1-butene. 3-bromo 1-butene. So this is one product that is formed, and along with that another product is obtained, that is CH2Br single bond CH double bond CH and here CH2H. That means here hydrogen bromide is added such that hydrogen adds to one carbon here and the bromine atom adds to a carbon which is far away from it. So if you take this as a first carbon, this becomes second, third, fourth. So it is known as 1 and 4 addition. So addition has taken place on carbon numbers 1 and 4. So this is called as 1,4 addition. This type is known as 1,4 addition. Remember, this is not the name of the molecule, not the IUPAC name. Actual IUPAC name is different, so you can name this IUPAC wise. What will it be? It is once again a substituted butene, but it is 2-butene. Double bond is on carbon number 2, so it is 2-butene. And there is a substituent bromo on this carbon, so which can be numbered as 1. So it is 1 bromo 2-butene. Okay, this molecule is obtained as another product. So we have a mixture of products which is obtained when you treat 1,3-butadiene with HBr. So this is the overall reaction. Now let us consider the mechanism of the reaction. So first step is electrophilic attack of H plus on one of the double bonds. This can be shown like this. If you consider addition of HBr here, hydrogen is electropositive, bromine is electronegative. So let us imagine that this bond or these pi electrons is going to be given to hydrogen, and during that time these electrons shift to bromine atom. So what do we get? We get CH2 CH CH, but now because these electrons have been given to H, this carbon is losing its electron and acquires a positive charge, and the CH2 C has now formed a new bond with the hydrogen. Okay. And with that Br minus is formed. Now this is a carbocation since it has got a positive charge on carbon. This carbocation can be stabilized by resonance because there is a pi electron here. It can help in the resonance of carbocation. So resonance structure would be, it would be like this. Shifting will take place here. So we get CH2 single bond CH double bond CH. Now because of the shifting of electrons, there is no positive charge on this carbon. Instead of that, the positive charge shifts to CH2 here. And of course, this remains as it is. Okay. So two carbocations are formed. First one is straightforward and second one is obtained by writing the resonance structure. So let me name this as A and this carbocation as B. This is step 1. Now if you see this step 1, we can notice that there are two types of carbocations here. Therefore, in the next step, when the addition of bromide takes place, bromide has two options. Either it can attack here or it can attack here. So accordingly, we can show it like this. CH2 double bond CH. CH plus CH2H. This was our carbocation A. Now it is attacked by the nucleophile. Nucleophile is Br minus. Now this, if it attacks carbon, we get CH2 double bond CHBr. So a new bond is formed with the carbon and CH2H. So carbocation A has resulted in this product, 1,2 addition product. And so let me write here, this has resulted in 1,2 addition. I will not write the name once again, it was written initially. And if the nucleophilic attack occurs like this, CH2 plus single bond CH double bond CH CH2H. This was our resonance stabilized carbocation B. This carbocation on attack of nucleophile, it will result in 1,4 addition. So we have to show it like this. So this results in 1,4 addition. So both the products are obtained. In fact, we get a mixture of the products. Now, even though we get the mixture of products, it is not 50%, 50%. One of the products will be major product and one of the products will be minor product. For example, if you carry out this reaction at 78 degrees Celsius, temperature is not 78, sorry, minus 78 degrees Celsius. At low temperatures, this 1,2 addition product will be the major product. We get 90% of this and the remaining 10% is 1,4 addition. However, if you go on increasing the temperature, the amount of 1,2 addition product goes on decreasing and 1,4 addition product goes on increasing. And when you approach about 40 degrees Celsius, that is slightly above the room temperature, the proportion is reversed. It becomes 1,4 addition becomes major product and 1,2 addition becomes minor product. So let us see what exactly happens. We can summarize whatever I told just now for the effect of temperature like this. CH2, CH, CH, CH2, addition of HBr, if you do it at low temperature, and on this side we do the reaction at high temperature. So at minus 78 degrees Celsius, CH2CH, CHBr and CH3. Instead of writing CH2H, I have written it as CH3. Okay, this mixture is there, but since the temperature is low, this is major product. And if we carry out the same reaction, addition of HBr at high temperature, once again the same two products are obtained. So I can just copy whatever is written on the left side. But now 1,2 addition is formed only around 10%, and 1,4 Br is missing here, so I've added that. So 1,4 addition product. Now this is the major product. So it varies, depends on the temperature. The question arises, why is it so? It is found that when the temperature is very low, the reaction is controlled by the kinetics. Kinetic factors control the reaction, and at that time, the product which has got a transition state of lower energy of activation, that kind of product will be formed easily. So here at low temperature, it is seen that this 1,2 addition product has got lower energy of activation. So it is formed easily. So the extent of formation is more. But as the temperature increases, the reaction is not controlled by kinetic factors. Instead of it, it is controlled by thermodynamic factors. So we say that the reaction is under thermodynamic control. When it is so, it is found that any product which is more stable will be formed in higher proportion. So if you compare these two products, you can see that this product is more substituted than this. In the sense, if you look at the double bond, here hydrogen is there. There are no substituents. Whereas here, for these two carbon atoms, this becomes a substituent. It is attached to carbon and hydrogen. So more substituted alkene will be dominating at higher temperature whenever it is under thermodynamic control. So that is about the effect of temperature. Let us now study second reaction, that is free radical addition. Earlier we have discussed addition of HBr, but it was simple addition, not in the presence of free radical. Now this is second reaction, that is addition of free radical to 1,3-butadiene. Example, we can take HBr itself. So once again, the reaction is similar. That is, in the sense the reactants are same, but now if it has to be free radical addition, the reaction has to be carried out in the presence of peroxides. In general, I can write the formula of peroxide like this. Anything which has got a OO linkage, that is peroxide. It acts as a radical initiator and it helps in the formation of free radicals. So HBr will be easily converted into H and Br radical. So I can write that step here, radical initiation. gives H and Br. This is the first step. So after this step, addition of the radicals takes place one by one, and once again we get a mixture of products. Here too we get two types of products. One is 1,4 addition, and the second one is 1,2 addition product. So the products are same, 1,2 addition product and 1,4 addition product. But in the presence of peroxides, it is observed that irrespective of the temperature, it is always 1,4 addition product which is dominant. So this is always the major product and this is the minor product. I can show the mechanism like this. So this is the first step, formation of free radical. After that, this pi bond undergoes homolytic fission in the presence of hydrogen radical. Okay, so imagine this is the homolytic fission results in two radicals, two free radicals, both on carbon atoms. Now, imagine that the radical which is formed on the first carbon, it forms a new bond with this hydrogen. So we get CH2 double bond CH, CH, CH. Now see here, since the homolytic fission had occurred, this carbon would have obtained a free radical. So dot is representing the free radical. And this carbon, which also had a radical, has now formed a bond with the incoming hydrogen. So a new bond is formed. So this is one radical which is generated in the mechanism of the reaction. This is an allylic free radical. It means if you see the position of this free radical, there is a single bond immediately next to it, and in the next position there is a double bond. So if the position of single and double bonds is like this, we call it as allylic. So this is a allylic free radical which is obtained. And of course, now this, suppose it reacts with the Br. Suppose it reacts with the Br, a new bond is formed with Br here, which results in 1, 2 addition product. This one. However, this free radical, it can show resonance. It can show resonance. You can show the resonance like this. Now imagine this pi bond undergoes homolytic fission. So one radical comes here, one more radical comes here, and these two can now form a pi bond. So the resonance structure would be CH2 dot single bond CH. The radical which was formed has now formed a new pi bond with the adjacent carbon. So it becomes like this, and H remains as it is, and then CH2H. There is no change over here as well. Now this is the resonance structure of the carbon free radical which was originally formed. Now suppose this particular form reacts further with the bromine radical, and that would result in a 1,4 addition product. Okay, so how are these two products formed? One is due to the attack of bromine on this original allylic free radical, and the second product would be due to the resonance free radical which is obtained, and then attack of bromine free radical. So 1,2 product or 1,4 product, both are obtained. But as I told you already, in the presence of peroxides, it is always the 1,4 product which dominates. 1,4 product. So 1,4 product means which one? This one, the first one. This is the major product. That is because this radical, this free radical where the double bond is in the center of the molecule, it is more stable. Similarly, this final product, sorry, this one, the first one, the final product is more substituted alkene when compared to this one. So this becomes the major product. So that is about the free radical addition reaction. Just one example. I will not write the mechanism for this. We took the example earlier for HBr. Instead of HBr, if you try some other free radical addition, like addition of trichlorobromomethane, Cl3CBr, trichlorobromomethane, it is found that once again it will result in two products. In this case, fission occurs like this. The first attacking species is CCl3. So attack of CCl3, first one, that's the first step. And after that has taken place, it will be attacked by Br. So what will be the mixture of products? One is CH2 Br CH H CH2 double bond here, and here CCl3. It is similar to our addition of HBr, but instead of H, it is Cl3C. So CCl3 is formed here, and bromine is attacking here. This is one of the products, and the other one is 1,2 addition, which gives us CH3, CH, CH2, CH2 double bond CH, single bond CH, single bond CH2. CCl3 has attacked first, so it will be like this, and bromine is attached here. So this is the second product. So this is the major product. This is the minor product. Now since you are adding another carbon atom here as well as here, and now it is no more substituted butene. Butene becomes converted into a substituted pentene. Both are substituted pentenes, and accordingly when you name IUPAC wise, all those substituents should be kept in mind. So this is the second example. All right. With that, we complete that particular topic, addition of conjugated dienes. Not complete, but only addition reactions which were mentioned in the syllabus, it is completed. So few more reactions of conjugated dienes we will study in the next video. Okay, so thank you. We will wind up this meeting.